Hello, everyone. Welcome to Episode 2 of our Automotive Cybersecurity Engineering course. Today, we're diving deep into understanding in-vehicle networks, focusing on communication protocols and security. This is part 2 of our network series, and it's designed for junior engineers with 1 to 2 years of experience. Over the next 11 minutes, we'll explore why modern vehicles use multiple network types, how they work, and most importantly, their security vulnerabilities and solutions. Let's get started. Before we jump in, let's outline what you'll learn today. First, you'll understand why vehicles need multiple network types. It's not just complexity for the sake of complexity. There are real engineering reasons. Second, we'll explain how the CAN protocol operates and its frame structure. CAN is the backbone of vehicle communication, so you need to know it inside and out. Third, you'll identify major security vulnerabilities in CAN networks. And trust me, there are plenty of them. Fourth, we'll compare FlexRay LIN and Automotive Ethernet. Each has its place in modern vehicles. And finally, you'll learn about network security controls like SecOC and MACsec, the solutions we use to protect in-vehicle communication. These 5 objectives will give you a comprehensive understanding of vehicle networking from a cybersecurity perspective. So why do vehicles need multiple network types? Why can't we just use one protocol for everything? The answer is simple. Different vehicle systems have vastly different requirements. Let's break this down into 4 key areas. First, speed requirements. Look at this range from 20 kilobits per second for LIN all the way up to 10 gigabits per second for Ethernet. That's a difference of 500,000 times. A simple door switch doesn't need gigabit speeds, but an autonomous driving camera definitely does. Second, real-time requirements. Some systems need deterministic timing, like FlexRay, where you know exactly when a message will arrive. Other systems can use best effort delivery, like Ethernet, where timing is more flexible, but you get much higher bandwidth. Third, payload size. CAN 2.0 can only carry 8 bytes of data per message. That's tiny, but Ethernet can carry 1,500 bytes or more per frame. If you're sending a high-resolution image from a camera, you need that large payload. Fourth, cost constraints. A low-cost LIN network might cost just a few dollars per node, but high-performance Ethernet with all its switches and processing power costs significantly more. Now, let's look at the comparison table at the bottom. LIN runs at 20 kilobits per second. It's perfect for simple sensors and switches like window controls or seat adjusters. CAN 2.0, the workhorse, runs at 1 megabit per second with 8-byte payloads. It's used for powertrain and chassis control, the core vehicle functions. CAN FD steps it up to 2 to 8 megabits per second with 64-byte payloads for enhanced control applications. FlexRay offers 10 megabits per second with 254-byte payloads, specifically designed for safety-critical systems like brake-by-wire. And Ethernet? It scales from 100 megabits to 10 gigabits per second with 1,500-plus byte payloads, perfect for cameras and ADAS systems. Each network type fills a specific need. That's why modern vehicles are a mix of all these technologies. Now let's dive into CAN, the Controller Area Network. This is truly the backbone of vehicle communication. On the left side, we have key features of CAN. First, it's a multi-master bus topology. What does this mean? Any ECU can transmit when the bus is idle. There's no single controller. Every node has equal opportunity to communicate. Second, it uses message-based communication. Here's something important. The CAN ID identifies the message type, not the sender or receiver. This is different from typical IT networks where you have source and destination addresses. Third, priority-based arbitration. When 2 nodes try to transmit simultaneously, the one with the lower CAN ID wins. Lower ID equals higher priority. This is automatic and happens at the bit level. Fourth, built-in error detection through CRC, cyclic redundancy check. The CAN controller automatically detects transmission errors. This makes CAN very reliable in harsh electromagnetic environments. Fifth, broadcast communication. All nodes receive all messages. It's up to each node to filter which messages it cares about. Now, on the right side, let's look at the 3 CAN variants. CAN 2.0, also called Classic CAN, is the most widely used. Maximum speed of 1 megabit per second, payload of 0 to 8 bytes. This legacy protocol is still in the vast majority of vehicles on the road today. CAN FD, which stands for Flexible Data Rate, bumps the speed up to 2 to 8 megabits per second in the data phase, with payloads up to 64 bytes. It's backward compatible with CAN 2.0, meaning they can coexist on the same network. CAN XL is the latest evolution. It can reach 20 megabits per second with payloads up to 2048 bytes. This is future-proofing for the increasing bandwidth needs we're seeing. Understanding these variants is crucial because you'll encounter all of them in modern vehicles. Let's break down the CAN message frame structure. Understanding this is essential for cybersecurity analysis. There are 4 key frame components you need to know. First, the CAN identifier, or CAN ID. This is either 11-bit standard or 29-bit extended. The CAN ID determines 2 things: message priority and message type. Remember, lower ID means higher priority during arbitration. Second, the data length code, or DLC. This field indicates the payload size. For CAN 2.0, that's 0 to 8 bytes. For CAN FD, it can go up to 64 bytes. Third, the data field, also called the payload. This is where the actual message content lives. It could be sensor values, control commands, status information, whatever the ECU needs to communicate. Fourth, the cyclic redundancy check, or CRC. This is the error detection mechanism. The CAN controller automatically calculates this based on the frame contents. If the received CRC doesn't match what the receiver calculates, the frame is discarded. Now here's the critical security limitation, and I want you to pay close attention to this red box at the bottom. The CAN protocol has no built-in authentication. None. Zero. The CAN protocol has no encryption. Everything is transmitted in plain text. All messages are visible to everyone on the bus. And here's the scary part: any node can send any message with any CAN ID. There's nothing preventing spoofing. This was designed in the 1980s for a closed, trusted environment inside a vehicle. But that assumption of trust is no longer valid in today's connected vehicles. This lack of security is exactly why we need additional security controls, which we'll discuss later. Let's talk about the real-world security vulnerabilities in CAN networks. These aren't theoretical. They've been demonstrated in actual attacks. First, message injection and spoofing. An attacker can send fake messages with any CAN ID they want. Since there's no authentication, any node can impersonate any other node. For example, an attacker could send fake speed readings, fake brake commands, or fake sensor data. The receiving ECU has no way to verify the message is legitimate. Second, replay attack. An attacker can capture legitimate messages from the CAN bus and retransmit them later. Because there's no freshness protection, no timestamp or counter, the receiving ECU will accept these old messages as valid. A classic example is replaying a door unlock command captured earlier. Third, denial of service, or DOS. An attacker can flood the bus with high-priority messages, effectively blocking all legitimate traffic. This exploits the priority-based arbitration mechanism. The attacker just sends messages with CAN ID 0 continuously. This can disable critical systems like ABS or power steering during vehicle operation. Imagine losing your brakes because someone is flooding your CAN bus. Fourth, eavesdropping. Since there's no encryption, an attacker can simply listen to all CAN bus traffic and see everything. All the data is visible in plain text. This can reveal vehicle behavior patterns, driver habits, or even proprietary control algorithms through reverse engineering. Now, these aren't just academic concerns. Look at the real-world impact at the bottom. In 2015, researchers remotely hacked a Jeep Cherokee and controlled the steering and brakes through the CAN bus. This led to a recall of 1.4 million vehicles. In 2016, researchers demonstrated CAN message injection on a Tesla Model S, controlling various vehicle functions. These attacks proved that CAN vulnerabilities are real, exploitable, and dangerous. This is why automotive cybersecurity is so critical. Now let's move on to FlexRay, a deterministic protocol designed specifically for safety-critical systems. Looking at the key features on the left. First, FlexRay uses time division multiple access, or TDMA. Unlike CAN's priority-based arbitration, FlexRay allocates guaranteed time slots for each message. If you're allocated time slot 5, you know you can transmit in slot 5 of every cycle. No competition, no arbitration. Second, deterministic timing. Message delivery times are predictable. This is crucial for safety-critical functions where you need to know exactly when a message will arrive. Third, high bandwidth. FlexRay offers up to 10 megabits per second per channel. That's 10 times faster than classic CAN. Fourth, dual-channel redundancy. FlexRay supports 2 independent channels. If one channel fails, the other keeps working. This provides fault tolerance for critical systems. Fifth, large payload. Each FlexRay message can carry up to 254 bytes. That's much more than CAN's 8 bytes. On the right, let's look at typical applications. FlexRay is used in steer-by-wire systems where there's no mechanical connection between the steering wheel and the wheels. It's all electronic. Brake-by-wire systems, also called electronic braking, rely on FlexRay for that deterministic, guaranteed delivery. Active suspension control needs the high bandwidth and determinism that FlexRay provides. And advanced driver assistance systems often use FlexRay as the backbone network. But here's the security challenge, and this is important. FlexRay still lacks native authentication and encryption. It's vulnerable to the same message spoofing and replay attacks as CAN. Even the time synchronization mechanism can be attacked to disrupt the entire network. So while FlexRay solves timing and bandwidth problems, it doesn't solve security problems out of the box. Let's talk about Automotive Ethernet, the future of in-vehicle networking. Why is the industry moving to Ethernet? Let me give you 4 compelling reasons. First, bandwidth explosion. Modern vehicles have multiple cameras, each generating 8+ megabits per second. Add LiDAR sensors, HD map data, and suddenly you need 100 megabits to 10 gigabits per second. CAN and FlexRay simply can't keep up. Second, software updates. Over-the-air updates are becoming standard. You can't push gigabytes of software over a 1 megabit CAN bus. You need fast, reliable data transfer that only Ethernet can provide. Third, cost reduction. Instead of running multiple separate CAN buses throughout the vehicle, you can use a single Ethernet cable for multiple functions. It's also lighter weight, which helps with fuel efficiency. Fourth, scalability. Automotive Ethernet is future-proof. You can start with 100 megabits and scale up to 10 gigabits as needs grow, all using the same basic architecture. Now let's look at the comparison table. Traditional CAN and FlexRay offer 1 to 10 megabits per second. Ethernet offers 100 megabits to 10 gigabits. That's 1,000 times more. CAN uses a bus topology. Ethernet uses a star topology with switches, which provides much better isolation and security. CAN has custom automotive protocols. Ethernet uses standard TCP/IP and UDP, which means we can leverage decades of IT networking knowledge and tools. Here's the key security difference: CAN requires add-on security like SecOc. Ethernet has native security built in: MACsec for layer 2, TLS for higher layers, IPsec for network layer. And the use cases: CAN is for control and sensors. Ethernet is for cameras, over-the-air updates, and advanced diagnostics. Automotive Ethernet brings the best of IT networking to vehicles. Now let's talk about solutions, how we actually protect in-vehicle communication. On the left, we have SecOc, which stands for Secure Onboard Communication. This is specifically designed for CAN and CAN-FD networks. How does it work? SecOc adds a message authentication code, or MAC, to CAN frames. Think of it like a digital signature that proves the message is authentic. It includes a freshness counter to prevent replay attacks. Each message has an incrementing counter, so you can't just replay an old message. SecOc authenticates everything: the CAN ID, the DLC, and the payload. The entire frame is protected. The challenge? It requires symmetric keys to be shared between ECUs. Key management becomes critical. On the right, we have MACsec, which is IEEE standard 802.1AE. This is designed for Automotive Ethernet. MACsec operates at layer 2, the data link layer. It provides both encryption and authentication. It protects against eavesdropping by encrypting the payload and against tampering by adding authentication tags. Replay protection is built in through packet numbering. Old packets are automatically rejected. MACsec provides point-to-point security between ECUs on the Ethernet network. Below, we have additional Ethernet security layers. TLS and IPsec provide transport and network layer security. These are commonly used for over-the-air updates and diagnostic communications. VLAN segmentation isolates different network domains. For example, the infotainment VLAN is separated from the chassis control VLAN. This limits attack propagation, and intrusion detection systems monitor for anomalous traffic patterns and alert on potential attacks. The key takeaway? Security must be layered. One control isn't enough. You need defense in depth. Let's talk about the real-world challenges of deploying network security. Theory is great, but implementation is hard. First challenge: performance impact. Cryptographic operations add latency. When you're computing a MAC or encrypting data, that takes time. Safety-critical CAN messages often have strict timing requirements, maybe 5 or 10 milliseconds maximum. If your crypto adds 3 milliseconds, you're eating up a huge chunk of your timing budget. That's why hardware accelerators, specifically hardware security modules, are required for real-time performance. Second challenge, key management complexity. You need to securely generate keys. You need to distribute them to the right ECUs during manufacturing. You need lifecycle management, rotating keys periodically, revoking compromised keys. And you need to protect those keys during manufacturing and service operations. This is one of the hardest problems in automotive security. Third challenge, backward compatibility. You can't just upgrade every ECU in the vehicle overnight. Legacy ECUs don't support SecOC or MACsec, so you end up with mixed security levels in the same network. Your gateway has to handle both secured and unsecured messages, which creates complexity and potential vulnerabilities. Fourth challenge, cost constraints. Hardware security modules add to the bill of materials cost. Development effort increases. Validation and testing take longer. And at the end of the day, you have to justify the return on investment for this security spending. It's a business decision, not just a technical one. So what are the best practices? Defense in depth. Layer multiple security controls at the network level, ECU level, and gateway level. Risk-based approach. Protect the most critical messages first. Brakes and steering are more important than seat heaters. Use hardware acceleration. Don't try to do crypto and software for real-time systems. And implement intrusion detection. Monitor for anomalies even when you have encryption enabled. Security is hard, but it's necessary. Let's bring it all together with a comprehensive comparison of the three main network types. Looking at speed, CAN 2.0 is 1 megabit per second. FlexRay is 10 megabits. Ethernet scales from 100 megabits to 10 gigabits. Payload size CAN has just 8 bytes. FlexRay has 254 bytes. Ethernet has 1,500 plus bytes. Topology, both CAN and FlexRay use bus topologies. Ethernet uses a star topology with switches. For determinism, CAN is priority-based, not guaranteed. FlexRay uses TDMA, which is fully deterministic. Ethernet uses AVB and TSN for time-sensitive applications. Redundancy, CAN has none built in. FlexRay has dual channels. Ethernet relies on network design for redundancy. Here's the security row. Pay attention. CAN and FlexRay have no native security. Ethernet has MACsec and TLS built in. For security add-ons, CAN and FlexRay can use SecOC. Ethernet can add IPsec and VLAN segmentation. Primary use cases, CAN is for control and sensors. FlexRay is for safety-critical systems. Ethernet is for ADAS and cameras. And here's the critical point. At the bottom, modern vehicles use all three networks simultaneously. Security must address each protocol's weaknesses and the gateways between them. The gateway is often the most critical security component because it connects these different worlds. Let's wrap up with 5 key takeaways. These are the things you absolutely need to remember. Number 1. Multiple network types exist because different systems have different requirements for speed, timing, and cost. It's not arbitrary. Each protocol fills a real need. Number 2. CAN protocol dominates in-vehicle communication, but it has no native security. It's vulnerable to spoofing, replay, denial of service, and eavesdropping. This is the biggest security challenge in automotive. Number 3. FlexRay offers determinism for safety-critical systems with its time division multiple access scheme. But it also lacks native security. Just being deterministic doesn't make it secure. Number 4. Automotive Ethernet brings IT security standards like MACsec and TLS to vehicles. It also provides the scalability we need for future bandwidth requirements. Ethernet is the future. Number 5. Security controls like SecOC for CAN and MACsec for Ethernet are essential, but they face real implementation challenges. Performance overhead, key management complexity, and cost constraints are all significant hurdles. Understanding these 5 points gives you the foundation you need to work on vehicle network security. Thank you for joining me for Episode 3. I hope you now have a clear understanding of in-vehicle networks and their security implications. If you have any questions, feel free to reach out to me at jackwang0210gmail.com. Up next is Episode 4, where we'll explore vehicle architecture evolution, how we're moving from distributed architectures to centralized domain controllers and zone architectures. Until then, keep learning, and remember every network protocol has security implications. Always think like an attacker. Thank you.